All right, today we're diving headfirst into one of the most bizarre, just plain reality-bending ideas in all of physics: quantum tunneling. It's a phenomenon that literally powers the sun. It makes the device you're using right now possible, and it seems to break the ultimate speed limit of the universe. So yeah, let's get into it.
First things first, let's get our heads around the basic idea. In our everyday world, things make sense. You roll a ball at a hill, and if it doesn't have enough energy to get to the top, well, it rolls back down. Every single time. The chance of it just magically appearing on the other side is zero. But down in the quantum world, phew, forget those rules. An electron hitting an energy barrier that it absolutely should not be able to cross has a real, non-zero chance of just popping out on the other side.
And this is what we call quantum tunneling. It's possible because at these tiny scales, particles like electrons aren't little billiard balls. They're more like waves of probability, described by the famous Schrödinger equation. So this wave doesn't just slam into the barrier and stop. A little bit of it actually leaks through. And that means there's a real calculable chance you'll find the particle on the other side. It's not magic, just some profoundly weird but very real wave mechanics.
Okay, but this is where the story gets really, really strange. You see, the fact that tunneling happens is settled science. We know it does. But when physicists asked what seems like a simple, logical follow-up question, they stumbled into a paradox that seemed to threaten the very foundations of physics.
So, the obvious question is, how long does this impossible journey actually take? It sounds straightforward enough, right? But here's the catch. In quantum mechanics, you can't just watch a particle travel through a barrier. The second you try to measure it inside the barrier, you kind of break the whole process. So physicists had to be clever. They calculated a time by tracking the peak of the particle's probability wave as it passes through. And the answer they got was, well, it was unsettling. What they discovered is something now called the Hartmann effect. For really thin barriers, the tunneling time gets longer as the barrier gets thicker. Okay, that makes sense. But then for thicker barriers, the time it takes for the peak of that wave to get through just stops increasing. It hits a maximum value and just stays there, no matter how much wider you make the barrier. It would take the same amount of time to cross a 5-nanometer barrier as it would a 10-nanometer one, which is just bizarre. And that right there is the problem. If you remember from high school, velocity is just distance divided by time. So if the distance is getting bigger, but the time is staying constant, the calculated velocity can get huge. In fact, for a long enough barrier, the effective velocity becomes faster than the speed of light, c, superluminal, which is supposed to be a massive no-no in physics. It's a direct violation of Einstein's special relativity. And look, this isn't just some mathematical weirdness on a blackboard. The Hartmann effect has actually been confirmed in experiments, over and over again, not with single electrons, which are too tricky to time, but with classical waves that follow the same rules. Scientists have measured this time saturation with microwaves, with photons tunneling across an air gap, and even with sound waves. The paradox wasn't just a theory, it was a real, physical puzzle that needed an answer. So, for decades, this puzzle just captivated physicists. Did quantum tunneling really break the cosmic speed limit? Well, let's get to the resolution and see how this amazing illusion was deconstructed, proving that causality, the law of cause and effect, is perfectly safe. So, did we break the speed of light? The short answer is a big, definitive no. Information, causality, they're not violated. The solution isn't some crazy new physics. It's actually a much deeper, more subtle understanding of what we're actually measuring when we even talk about tunneling time. The paradox, it turns out, is a flaw in our everyday language, not in the laws of physics. Now, this table really gets to the heart of the problem. It turns out there are actually several different ways you can even define a tunneling time, and they don't all give you the same answer. The paradox only pops up when you use one specific definition, the group delay, which is the one that tracks the wave's peak. Other ways of thinking about it, like dwell time, don't lead to this superluminal weirdness. And that was the first huge clue. The problem is tied to a specific and maybe even misleading definition of time. So here's how modern physics completely resolves this. It's kind of a three-part answer. First, that group delay time, it isn't really a travel time at all. A better way to think of it is as the lifetime of energy that gets stored inside the barrier. Think of the barrier like a sponge soaking up energy. It absorbs a lot at first, but it can only hold so much before it's saturated. The barrier's energy storage hits a maximum, and that saturation perfectly explains the Hartmann effect without anything traveling faster than light. Second, you can't actually send a signal, information, faster than light.
That's because the real information arrives with the very front of the wave, not its peak, and that front never breaks the speed limit. And finally, the barrier itself acts like a filter. It tends to let the faster, higher energy parts of the wave packet through more easily. So this reshapes the wave, making the new peak appear on the other side earlier than you'd expect. It's an illusion of speed, not a real acceleration. Okay, so with the paradox put to bed, we can finally appreciate tunneling for what it is. Not some cosmic loophole, but a fundamental process that nature and our own technology have been using all along. So let's see how this impossible leap powers pretty much everything.
Far from being some obscure thing that only happens in a lab, quantum tunneling is actually a core engine of the natural world. Seriously, without it, the universe would be a completely different and much, much darker place. Take the sun. The temperature in its core, believe it or not, isn't actually high enough for protons to overcome their mutual electrical repulsion and fuse together. The only reason the sun shines is because those protons can tunnel through that repulsive barrier. And it's the same story with radioactivity. Some elements decay because alpha particles literally tunnel out of the atomic nucleus, escaping a prison they classically should be trapped inside of forever. And this quantum weirdness isn't just out there in the stars, it's right here, probably in your hands or on your desk right now. The entire foundation of modern digital storage and high-speed electronics relies on engineers being able to precisely control this tunneling effect.
Every single time you save a file to a flash drive or an SSD, billions of electrons are tunneling through a tiny insulating layer to store a bit of your data. It's happening in things like tunnel diodes, and it's the core principle behind Josephson junctions, which are the heart of the world's most sensitive magnetic detectors and many leading quantum computers. But perhaps the most mind-blowing application of all is the scanning tunneling microscope, or STM. What this thing does is it uses a tiny, atomically sharp needle that just hovers nanometers above a surface. Then, electrons actually tunnel across the vacuum of space between the tip and the surface, and that creates a measurable electrical current. And here's the genius part. That tunneling current is incredibly sensitive to distance. By measuring it as the tip scans across the surface, the STM can map the topography with such unbelievable precision that it can create images of individual atoms. It's the tool that finally allowed humanity to truly see the atomic world. It just changed everything. So this all brings us to the future. You see, for decades, engineers pretty much tried to suppress and fight against weird quantum effects. But the next big technological revolution is about a complete shift in that philosophy. And this slide just sums it up perfectly. In a normal computer chip in your laptop, electron tunneling is a bad thing. It's a current leak that wastes power and creates heat. Engineers work really hard to stop it. But in a quantum computer, that exact same tunneling effect, when you control it precisely, becomes the main feature. It's what allows a qubit to work. The future is about leveraging these effects, not fighting them. A bug becomes a feature. And this way of thinking defines the next frontier. We're talking quantum computers built from tunneling-based qubits. We're talking about nanotechnology that aims to build circuits out of single molecules, where tunneling is the only way for current to even flow. And we're even talking about using quantum computers to simulate tunneling itself, to help us design better solar cells or new medicines from the ground up. So really, the story of quantum tunneling is the story of physics in a nutshell. It starts out as this baffling, mind-bending paradox that seems to break all the rules. But through deeper and deeper understanding, it transforms into a predictable, controllable, and absolutely indispensable tool for understanding our universe, and more importantly, for building its future. And that leaves us with this final massive thought. For almost all of human history, we've built things using classical rules that work for big objects. But we are now right at the dawn of an age where we can build things atom by atom, using the strange and powerful rules of quantum mechanics. So the real question for the next 100 years is, what happens when we finally stop fighting these effects and truly start building with them? The possibilities are just staggering.